LearningMeasure.tv, science and engineering podcast with emphasis on measurement. Brought to you by David Archer and LearningMeasure.com. Episode 15, Mesh Current Analysis. Hello, I'm David Archer. I'm the owner of LearningMeasure.com and LearningMeasure.tv. This podcast is sponsored by TradePub.com, GoToMeeting.com, and is part of the Blueberry community of podcasts. Check out Blueberry. There's a lot of interesting podcasts there. Anyway, as always, we're going to say a little bit about my other part of this, LearningMeasure.com. LearningMeasure.com is a subscription-based training website associated with this podcast. When you register with LearningMeasure.com, you get 2 weeks free, and after that, you have access to all the training materials for $5 a month, training courses, and gives you the opportunity to post your resume, have others view your training record, and all that as well. Also, I want to announce that last week a new course was added, EE 121, Intermediate DC Circuit Theory. This course was developed because one of you sent me an email saying you wanted a course and maybe want me to talk something about some of the subjects in that course, and that's what this episode is going to be about. Actually, somebody asked for it, so we're going to give it to you. Okay, so the topic, what we're going to talk about in this episode, is the mesh analysis of DC circuits. If you remember way back to episode -5, which was our first episode, we talked about the measurement cycle, that how you, sometime before you make a measurement, you have to make a prediction. Well, analysis of circuits usually gives you a prediction, or you might have a situation where you have some device that you can't measure, but you can measure the components, and later on you can do an analysis to come up with a measurement equation for what the result is based on the components. That's the connection to measurement with this topic. It's really a topic of electrical engineering, but yeah, we will talk about that. But before we get there, okay, and the other thing we're going to talk about in this episode, what we're going to talk about the mesh analysis only applies to planar circuits. We'll tell you about that in a minute. But before we do that, for those of you who aren't electrical engineers, we're going to go over some of the fundamentals of DC circuits. There's a thing called current, basically the flow of electrons, you know, in the wall. When we're talking about DC, we're talking about direct current, which means it doesn't fluctuate with time. So in circuits, you can have wires that carry current. And there's something called Kirchhoff's current law. It says, well, if you have currents entering and leaving a junction, let's say I1 entering and I2 and I3 leaving, just say arbitrarily here, it must be the case that the sum of the currents entering and leaving the junction minus, so it must be the case that that's 0. Because in the junction, all that's basically saying is that current's not created in the junction. Electron comes in here and it sort of goes one way or the other. It's exactly, in DC circuit analysis, you sometimes use water analogies. Think of it this way. If you had a pipe with a T like this, and you dumped water into it, you had dumped some bucket of water, you dumped water into here, well, and you collected the water down here somehow. The water's going to go and split and go 2 directions, and what the water you end up with is going to be the same as what you put in. No water is created in the pipe in the exact same way. No electrons, or moving electrons are created in a junction of wires. I mean, it's true even if there's not more than one wire. I mean, if there's just a point on a wire, it has to be that the current coming in is equal to the current going out. Nothing, it's called Kirchhoff's current law. Doesn't sound all that, it's fairly intuitive. It says you can't get something for nothing in the area of electric current. Because if you did, nobody would be billing us for our electricity. Anyway, an economic argument why charge is conserved. Anyway, the other one is if you have some circuit, no matter how complicated, you have some resistors. These are symbols for like resistors and batteries. And, you can have some sort of complicated thing with all kinds of branches and resistors everywhere. No matter how complicated, I keep drawing and drawing and drawing. But if you look at the voltage drops, you start from here, figure out the volt, call this 0, some point in the circuit. Well, let's say this battery's V, there's some voltage V here. There's some voltage drop across this resistor, some voltage drop across this resistor, and then you get back to here. Well, if voltage has any meaning, when you get back to here, you should be at the same value you were when you started. So you have basically Kirchhoff's voltage rule that whenever you have a loop in a circuit, if you sum up the voltage drops going around the circuit, in each loop of a circuit, it must be 0. Nothing tremendously remarkable there. It's just a statement that voltage means something in DC circuits. Because it's the same thing as with water analogy. You have pumps, right, that circulate water, and it might have some sort of something in the way, like a thing filled with sand or something. And you have something called pressure. Well, the pressure's higher here and lower here, but if you start here, you go around, the pressure will drop when you go through there. And eventually, if you start at one point and come back to the other point, pressure has to be the same if it has any meaning. There's the same sort of law in the case of water analogies. So we've got two laws now, Kirchhoff's current law and Kirchhoff's voltage law. By the way, since I didn't say that, for the symbols, DC circuits, a resistor looks like this. Some of you are used to just seeing a box with some sort of, like 100 ohms in it. That's another way, but this has been around longer. And then a line is a wire, and a battery is something that looks like this. Okay, usually has a plus and minus. Okay, so we all are familiar with batteries, I think, and resistors. Maybe not so much resistors, but the thing about resistors and currents and voltages is there's a relationship between them. So if you have a resistor hooked up, let's say, to a battery, a voltage V, and a resistance R, resistance is measured in ohms, voltage, current, this is measured in volts, current I, measured in amps. There's a relationship between them. V equals IR. A few episodes back, we had an episode on Ohm's law. This sometimes is called E for electromotive force, so this could also be E equals IR or V equals IR. The other thing is power. We've talked about that before. P, power delivered. So we got, well, that's right at the way it was in the previous episode. Ohm's law. And then P, power delivered to the resistor. We've seen this before in previous podcasts. Is I squared R. That and Kirchhoff's voltage law and Kirchhoff's current law pretty much is it. That's all of DC circuit analysis. You can stop there. Everything else is just some method to solve complicated problems. how to apply the mathematics, for instance. But the sum total of DC circuit theory are these two equations and Kirchhoff's current law and Kirchhoff's voltage law. There's nothing else. The rest of it's mathematics, essentially. Okay. Now we're going to pay a little bill. Okay. If you waste hours in traffic to get to clients' offices for meetings, or spending more times getting to meeting than actually meeting, and that can't really be productive, there's great news. There is an easier and more affordable way. GoToMeeting. The award-winning service lets you hold meetings over the internet with people in multiple locations. Just log on to gotomeeting.com and start meetings with a click. Instantly, everyone sees your computer desktop on their computer screen. It's like meeting in person, but less expensive and less time-consuming. Hold unlimited meetings for one flat rate. Meet from your home office, hotel room, anytime, anywhere. Try GoToMeeting free for 45 days. Just visit gotomeeting.com/podcast. That's gotomeeting.com/podcast. Do more and travel less with GoToMeeting. Okay, now let's talk about the mesh method. Okay, first of all, it only applies to planar circuits. Planar circuits are circuits that can be drawn on a plane with no crossing wires. In other words, if the circuit requires a third dimension to make connections, you can't use this method. There's other methods you can use. Like I said, this method is just something you can use to analyze circuits, which is no more content than this and Kirchhoff's laws, but it's a way to use them to solve for unknown currents in a circuit. Let's draw a simple circuit. Let's say let's randomly generate some circuit. Let's say we have a battery, and let's say, I don't know, a resistor. And let's put another battery here. And another resistor. Okay. And what you do is you start out, okay, you have a circuit. Now, first thing you want to do is identify principal nodes of a circuit. Principal nodes of a circuit are places where more than one wire is connected. Now, here's one. We'll label this node 1. Okay. And this here, since it's all connected to wires, is really just one big node. We'll call it N2. Okay, and those were places you can get voltages. Those are principal nodes. You could have other nodes, like if you wanted to know the voltage here, and you pick one as a reference. We'll call this the reference node. We'll call it voltage equals 0, because you need to have some reference. Okay, so now that we've done that, that's places we want. Nodes are places where we want to know voltages. Well, we can figure that out later. The way this works is, okay, you just use, let's call this V1, so we can sum voltage, make it quite general. Call this V2, call this R1, call this R2, and call this R3. Okay, just so we call it that. The first step in the mesh current method is to arbitrarily assign loop currents to each loop. So you say, okay, I'm going to call a loop, and you just arbitrarily pick a direction. We'll call this I1, and what the heck, we'll arbitrarily pick the same direction and call this I2. Okay, these unknown currents are what we don't know. That's what we're trying to find out. Well, what you do is you start here and you go, well, current goes from minus to plus, so the polarity for this current on the resistors, the voltage drops across the resistors is like that. Now, if we pick a direction and it's wrong, which is okay, we're going to come up with a negative current for an answer. So it doesn't matter which direction you pick. You can pick any direction. Here I just picked clockwise just because I did, which is pretty normal. You can always pick clockwise or counterclockwise, or if you want to be fancy, you can make each of them go a different direction. It doesn't matter, but generally it's good to just pick one direction and be done with it. Okay, so now you apply the Kirchhoff's voltage laws to the first loop, starting with here, I guess. And so we go, okay, we got V1, and then since this is plus minus, these are adding up, plus I1, R1, and then here, there's two currents going through this resistor relative to this one. This one's negative compared to this one. So you got to look, this is I1 minus I2. So the voltage drop here is R2, I1 minus I2, which according to the Kirchhoff voltage law is 0. Okay, well, let's look at this other loop here. Okay, let's start here again, this node here, just for fun. So in this loop, this is minus and this is plus. And so this is minus and plus. Because, you know, current flows. If the current's flowing this way, the voltage drop, the current goes from minus to plus. Always. So here we've got, so this is plus minus. So this first voltage is I2 minus I1. So it's I2 minus I1 R1, or R2, sorry. This is going the opposite way, so it's minus V2. And then this last one is just I2R3 plus I2R3. Okay, well, what have we got? Let me write this so it's easier to see. So we've got V1 plus I1 R1 plus R2. Let's do a little algebra, grouping things a little different. Minus I2 R2 equals 0. Again here, let's regroup these terms. So we've got minus V2 plus, minus I1 R2 plus I2 times R2 plus R3. So what we have is two equations in two unknowns for the unknown currents, which we can solve. That's a fairly straightforward thing to do, systems of equations. We won't go into systems of equations in this podcast. We might do it in another one someday. But anyway, what you do need to solve for n unknowns is n independent equations. And what this has done is generated two independent equations for two unknowns. Well, this is kind of a little arbitrary circuit. Let's look at a circuit that's actually something that many of you may have seen. It's something that is important for measurement for sure. And it's for trivia question. What circuit, for the electrical engineers, what circuit out there is topologically equivalent to a tetrahedron? That's right, it's the Wheatstone bridge. So we're going to talk about an unbalanced Wheatstone bridge. That's what this circuit I'm going to draw is called. very complicated, well, complicated mathematically to handle by just sort of writing equations, which will. So you have some voltage across this thing. And you got 5 resistors. R1, R2, R3, R4, R5. Well, you might think this is hopelessly complicated. This circuit has 1, 2, 3, 4, 5 branches, 6 branches. They all have different currents. You might think there's six equations here, but there isn't. If you look to mesh analysis here, this is written on a plane. You can, okay, let's call this, let's put a current here. I1 in this loop, another current here, I2, another current here, I3. Okay, so just draw the arrows so we know which way things are going. Okay, now what do we've got? Well, we've got three unknown currents, and once we solve for the 3 unknown currents, we know we can use Ohm's law to determine the voltage everywhere. We can use this law to determine power delivered everywhere. So all we need to know is what are the 3 currents. Well, we can solve this. Again, let's see, in this loop, you've got the first equation, V plus, okay, these are opposites, so I1 minus I2 R1. The second part here, plus, this one's in plus minus, right? So these are all in series. Voltage drops the same sign. This is I1 minus I3. Okay, I'll move this over here so we have room. Times R2 equals 0. Okay, well, there's one equation. Look at this loop. Okay, again, for this loop, the polarities are like this. So everything's just all nice. So you've got I3 minus I1, R2, voltage drop in that R2, plus voltage drop here. Well, they're going opposite directions again. I3 minus I2 R5. And the last one is I3 R4 equals 0. Okay, we have one more loop. Let's look at this one here. Same thing, okay. Minus plus, everything adds up. So we've got I2 minus, since it's going this way, this is going this way, they subtract again, minus I1 R1. Plus I2 R3 plus, okay, I2 minus I3 R5 equals 0. Okay, we have 3 equations, 3 unknowns. We can solve that. You can use any number of mathematical tools like MATLAB or Octave, which is an open source MATLAB clone, or Mathematica, or any number of packages can solve systems of equations, or you can do it manually. 3 by 3 is not too hard to solve manually. But again, you now can solve for all the unknown currents. You can know what all the voltages are. In particular, you can figure out if this thing is unbalanced, what's the voltage here? What's the current here? What would it take to balance the bridge? There's all kinds of things you can do with this. Anyway, we'll leave that at that right now, and we'll come back after this short ad.
One of LearningMeasure.tv's sponsors is TradePub.com. TradePub.com is a site where one can sign up for a large number of free trade publications. If you'd like to support this podcast, go to the LearningMeasure.tv site, scroll down to the free publications link, and choose one of the magazines or one of the publications or one of the categories and sign up through that link. Each publication subscribed to through this link on LearningMeasure.tv website helps keep Learning Measure TV on the air. Thank you for your support.
But if you're, last week, my oldest daughter went off to college to UC Irvine. So I hope she's having a good time. We are interested, and if you're a college student, we would love to get your feedback on what kind of questions you might want to ask. If you want to ask something about a homework problem, basically ask anything. We'll choose which ones to answer. Ask anything you'd like. Or anybody else, if you're not a college student, if you're an engineer or scientist or technician, that's where college students, that's who we're looking for. And you have any question about any topic whatsoever, send me a question at questions@learningmeasure.tv, and we'll try to answer them on the air. It could be a homework problem, it could be an engineering problem, it could be some sort of measurement problem. This is a measurement-related podcast, so we prefer that measurement-related questions or just science and engineering-related questions. But, you know, send us whatever question you want, and if we decide we're going to answer it, we'll answer it for you. Okay? If it looks like it's something that might be of value. I mean, you can ask whatever you want, but we'll see what we put on the air. Again, if you have any suggestions for what you want to see on this podcast, what episode, what kind of topics you'd like covered, I'd like to just go over a wide range of subjects. And if I don't know the answer to something or don't know how to the subject you want to see, I'll find out about it. I'll try to get somebody to help put something together. So if you have a suggestion, send an email at suggestions@learningmeasure.tv, and we'll try to do something about that. Finally, if you are a vendor of test equipment or software, or you're a consultant and you wouldn't mind advertising yourself on this podcast, if you're in the Las Vegas area and we can prearrange it, we'd love to have you on the podcast. We can't pay anything, and we don't want any pay in return for the advertisement. But if you're here, we would love to interview you or have you do a sales pitch or whatever. Just send us an email at vendors@learningmeasure.tv. Okay, well, that's it for this episode. It's a little short. Didn't have that much time to prepare with moving my daughter into college and other events that were happening in town, but hopefully we'll have a little longer one next time. All right, I'll see you next time.